How's everyone doing today? Happy Friday, everyone. Good to hear. Good to hear. Alrighty. So, since it is Friday and all, I'm gonna try to make today nice and quick. It's pretty simple what we're going over today. So, I'll try to be brief about it. Imagine me being brief, though. Lol. Okay. All right. So today we're going to go over the many chain rules in multivariable calculus, but they all basically boil down to sort of the same idea. Okay, so basically, the idea here is, so you have a function of a variable or multiple variables. So we have a function that's like ostensibly of, certain number of variables, but each one of those variables is a function of other variables. So for example, suppose we have some function, let's say t of xy. And suppose this gives you the temperature at point xy. So you pick a point in the plane, xy. This function gives you the temperature at that point. Suppose, however, that we're moving along some circle. So let's say the unit circle counterclockwise. According to the parameterization, x is cos t, y is sine t. So suppose we have some particle moving along this beautiful, extremely circular circle here. According to the x coordinate at time t is cos t, the y coordinate at time t is sine t. So now, we'll say this is x of t. This is y of t. Let me write it like that instead. That's fine. So x and y themselves are both functions of t now. So we can actually think of the temperature now as being a function of t. You can specify some time, t, and at some, that'll give you a position. You just plug in t into cos t for x, sine t for y, and then you can see the temperature at time t. So we can actually now think of temperature as being a function of little t, time. And so we can talk about the rate of change of temperature with respect to time. And to calculate that, we would have to use a chain rule. So there are infinitely many different chain rules because the chain rules are going to be different depending on how many variables your function is of. So in this case, our function is a function of x and y, sort of ostensibly. So it seems to be a function of two variables, but each of those variables is a function of one variable. And of course, we can change the number of, so we could initially have a function of 3 variables, and each of those is a function of 2 variables, et cetera. Like there are any number of combinations, and each of these lead to different chain rules. But there's a nice simple rule we can use to determine all the chain rules. And basically, it just comes down to drawing a tree. Okay, so let's look at an example. So suppose f is a function of x, y, and z, and x, y, and z are each a function of s and t. So f, if you make the substitution, so x is actually a function of x and t. So every time you see x in your original function, f of x, y, z, you can replace it with x of st, the function of s and t that x is. So you can replace x with s's and t's, y's with s's and t's, z's with s's and t's. So you can think of f as actually, this is just an example. So I'm not even like specifying what the, we'll do like an example with actual functions, but I'm just saying, suppose they're not two random variables, like they're just two other variables. Like, yeah, we'll do an example in a second. I think it'll clear it up, any confusion you might have. So if you plug in x, y, and z with their functions of s and t, we can actually write f as a function of s and t. So f is actually a function of s and t. So we can talk about the partial of f with respect to s and the partial of f with respect to t. So the way we're going to do this is we're going to draw a tree. So we have f up at the top. F is initially written as a function of 3 variables, x, y, and z. And so these are sort of like not the actual independent variables. X, y, and z are not the things that are changing here because they each depend on s and t. So these are the intermediate variables. Let me give myself room. So we call these guys the intermediate variables. X, y, and z. And the actual independent variables are s and t. the things we're actually plugging in to get our function. So f is written initially as a function of x, y, and z, but x, y, and z are each functions of s and t. So draw your tree like this. F is a function of x, y, and z, your intermediate variables. In each of those, we need to have an s and t. Okay, so for the partial of f with respect to s, what we're going to do is we're going to start at the top of our tree and look at all the ways we can go from the top down to s at the bottom. So from f down to s. So we can go from f to x to s, f to y to s, and f to z to s. So between each of these variables, we have a derivative. So from f down to x, label that node as df dx. From x down to s, label that dx ds. And then do the same for the others. F down to y, df dy. And from y to s, that's dy ds. And then similarly, f down to z. After you've done this enough, you won't need to actually draw this tree out and write all this. But this is just, sorry, to explain what's going on. So sorry, f down to z is df dz. And z down to s, dz ds. Okay. So we're going to look at each path from f down to s. And we're going to multiply down and add up all the paths. So there are three different paths, right? So we can go from f to x to s. So we're going to multiply down df dx times dx ds. And then do the same for the other two paths. And then we're going to add them all up. So f down, whoops, f down to y, down to s. So we have df dy, dy ds. So df dy times dy ds. And then do the same for the other path. F down to z, and then z down to s. Df dz times dz ds. So then we add these guys up. And that is the expression for the partial of f with respect to s. So draw your tree. You have f, your intermediate variables, and under each of those, the actual dependent variables. And then look at all the ways you can go from f down to whatever variable you're taking the derivative with respect to. So for df ds, we look at all the ways we can go from f down to s, multiply down, and then add up all the paths. And then we can do the same for df dt. And the process works exactly the same. So we can go f to x to t. So that's df dx. And then from x to t is dx dt. And then f to y to t, df dy, dy dt. And then from f to z to t, df dz times dz dt. And that's going to be the process for every single partial derivative we take. Or every single, sorry, chain rule we take, derivative. Okay, any questions about this? Because this process is basically the entire chapter. If you understand this, you know almost everything except for the stuff at the very, very end. Sorry, those are all supposed to be the fancy D's for partial derivatives. Some of them, many of them look like 2's. My apologies. They're all D's. Also, I wanna clarify something. So it's not a big deal, but so suppose we had in our initial example, I said, okay, so t was a function of x and y, but x and y were each a function of little t. Right, so in this example, notice I didn't use the fancy d here when I took the derivative. So I can talk about d capital T of d little t. So I use the normal d here because t is actually a function of one variable, little t. Maybe using 2 t's was a mistake here, but you get the idea. Really, t is just a function of one variable, so there's only one derivative we can take. And when we have a function of one variable, we use the normal d. We just do, that's how we do it. And so if we were to do it, if we were to write this out, this would look, if we draw our tree, let me do this real quick, just to illustrate what I'm trying to talk about. So t is a function of x and y, and x and y are each a function of just t. Okay. So the derivative of big T with respect to little t would be, so we can go from t to x to little t. So t is initially written as a function of 2 variables. So we take the partial of big T with respect to x, so t to x, but then x is just a function of one variable t, so that's times normal dx, normal dt. And then we can go from t to y to t, so that would be the partial of big T with respect to y times y is just a function of one variable t, normal dy, normal dt. So honestly, not a huge deal if you always use fancy d's or normal d's or whatever. But we use, like, if you're taking partial, you do partial derivatives if you're a function of more than one variable, or if you're treating it as a function of more than one variable. And then normal d's if we use the fancy d's for the partials, and the normal d's if you're just a function of a single variable, or you're treating it as a function of a single variable. I don't want to dwell too long on that, but I hope I don't think we'll run into that anymore today, but I just wanted to clarify that. But if that was confusing to you, don't worry about it. I don't think you're ever going to get any points taken off for using a fancy D when you should have used a normal D or otherwise. It's just a notation thing. Okay. So here's an actual example with actual numbers. Suppose f of xy is e to the xy. And suppose x and y are both functions of s and t. X is st and y, oh, sorry, st and u. Y is s minus ut squared. So we want to calculate the partial of f with respect to t. So f is a function of x and y, but x and y are each functions of st and u. So f is really a function of st and u, so we can take partials with respect to st or u. So we want to know the partial of f with respect to t. At 2, 3, negative 1. So s is 2, t is 3, u is -1. Okay. So we're going to draw our tree. F, let me give myself a little more room here. So f, we initially treat as a function of x and y, so e to the xy. But x and y are each functions of s, t, and u. So we want df dt. So the partial of f, let me try to make these at least, try to make them look like d's. So we're going to look at all the ways we can go from f down to t. So we're going to look at all the paths, multiply down, and add up the paths. So from f to x, we got our df dx. And from x to t, we have our dx dt. From f to y, we have our df dy. And from y to t, we have our dy dt. So multiply down the path. So df dx times dx dt. And then add the other path, df dy, times dy dt. So so you can be so we're still treating x as a function of s, t, and u. It's just u doesn't show up in the function, right? So like remember so we could have so suppose we looked at the we treat, say, the function let's say x squared, or sorry, let's say let's say consider like the function 0, right? If we look at the graph of the function 0, z equals 0, right? So that's still, we treat it like as a function of x and y, even though x and y don't show up. Like z equals 0, if you graph it, you get the entire xy plane. And so you can graph it as a function of two variables. You get a surface, even though neither of those two variables actually show up. So yeah, we're treating x as a function of s, t, and u, even though u doesn't show up. Yeah. So yeah, the only way we can make this work is if each of the independent variables, or each of the intermediate variables, are functions of the same independent variables. Otherwise, we can't really make this work. Okay. So all right. So the partial of f with respect to x. So f is e to the xy. What's the partial of f with respect to x? What's the partial of what's the derivative of e to the xy with respect to x?
It's e to the xy times y.
Right, right. So we get y e to the xy. And then what's the partial of x with respect to t? So x is equal to st. What's the partial of st with respect to t? We get s, right? And then we do the same for the other. So df dy. So the partial of e to the xy with respect to y is x e to the xy. And the partial of y, which is s minus ut squared, with respect to t, is -2tu. Or sorry, -2ut, let me say. Same thing, but. Okay, so so we wrote down kind of the general form for the partial of f with respect to t, but we're given a specific point. And if I want to emphasize that, so if you're given a point to evaluate your derivative, you need to, at the end, get a number. I mean a number. There should be no variables involved whatsoever. And let me show you why I'm emphasizing this, because this is a common mistake I see in exams. So let me rewrite this. So we got y e to the xy times s plus x e to the xy times negative 2ut. So we want to evaluate this at I think it was 2, 3, negative 1. Yes. So s is 2, t is 3, u is going to be negative 1. And so where you see s, u, and t, you can just plug in s equals 2, t equals 3, u equals negative 1. But notice we have x and y. And if you're evaluating a derivative at a point, you should not see any variables anywhere. So what do we do about the x and y? Well, those need to become numbers as well. So to figure out what we plug in for x and for y, we go back to their expressions in terms of s, t, and u, and then we plug in s equals 2, t equals 3, u equals negative 1. So at s equals 2, t equals 3, u equals negative 1, what is x?
Six.
I think I heard 6, right? So x would be 2 times 3, which is 6. And then similarly, y would be 2 minus negative 1 times 3 squared. So 2 plus 9 would be 11. So where we see x, we're going to plug in 6. Oops. And where we see y, we're going to plug in 11. So we get y e to the xy becomes 11 e to the 6 times 11, which is 66, times s, which we said is 2, plus x e to the xy becomes 6e to the 66. Negative 2ut becomes negative 2 times negative 1 times 3, becomes positive 6. So we get 22e to the 66 plus 36e to the 66. We get 58e to the 66, which is a number. We want to end up with a number at the end. You should not have any variables anywhere in there. Right. So remember always to write your intermediate variables as numbers by plugging in your s, t, and u, or whatever the independent variables are, into the formula. Does everyone understand that point? That's important. Okay, so that's pretty much every chain rule problem. Let's look at how we, let's use a chain rule to get some nice formulas for implicit differentiation. So I don't believe we haven't done any implicit differentiation yet. And the reason is probably because there's a sort of a long way to do it like we do in calculus 1 and 2. But there's actually a nice, much shorter way of doing it, which we can derive using the chain rule. Whoop, can't spell. Differentiation. Okay, so if you remember back from 140, suppose we have an expression, so an equation involving x and y, but you can't necessarily get y by itself. Suppose you had like x squared plus y squared equals 1, right? So if you change x, y also changes because it has to satisfy the equation x squared plus y squared equals 1. So you can think of as y being implicitly a function of x, right? You can't get y by itself and say y is equal to this one function of x, but y is thought of implicitly as a function of x. So we can do the same for z being a function, say, of x and y, or more variables. But suppose, for example, we had the equation x squared plus y squared minus 2z squared minus 8z minus 4 equals 0. No, sorry, minus 8x. Is it? Oh, sorry, no, I missed, okay. Sorry, all right, I miswrote this. Did not write this correctly. It's, sorry, plus 12x minus 8z minus 4 equals 0. There we go. Okay, so this is an equation. This gives us, you can check, gives us a, when you move stuff around, you get a hyperboloid of 1 sheet. I won't explain that any further, but so you can't get z by itself, clearly here, writing it as a function of x and y. But z is defined implicitly as a function of x and y. So it's you think of it, even though you can't get z and write it specifically, explicitly as a function of x and y, we think of it as a function of x and y. So you can take the partial of z with respect to x and the partial of z with respect to y. So the way we would do this in 140 and 141 was we would take the derivative of both sides with respect to x. So that's easy for x squared, that's easy for y squared. And then for minus 2z squared, we think of z as a function of x and y. So we'd use the chain rule, minus 2z squared would become minus 4z times dz dx, et cetera. And then you would proceed to get dz dx by itself. But there's in fact an easier way, a much quicker way of calculating the partial z with respect to x and the partial z with respect to y using the chain rule. So what we're going to do is we're going to get everything on one side, and we're going to write that whole thing as big F of x, y, and z. So put everything on one side. That's going to be your big F of x, y, z. So a big F of x, y, z. And we're going to treat x, y, and z. So we're treating z as a function of x and y implicitly. So we're going to treat x and y also as functions of x and y in a really obvious way, right? X is a function of x and y. It's just x, right? So what's the derivative of the function x with respect to x? Well, treating y as a constant, taking the derivative with respect to x, you get 1. What's the derivative of y with respect to x? So if you have the function y, you take the partial with respect to x, what do you get? So if my f of x, y is equal to y, and I take the derivative with respect to x, what am I going to get? You get 0, right? But we can treat y as just the function y and take the derivative with respect to x. Okay, so we're going to derive our equation in this way. So big F is a function of x and y. So we can take the partial of f with respect to x. And we go down our tree. We can go from f to x to little x, or f to x. So df dx, dx dx. So the partial of the function x with respect to x. And then we can go from f to y to x. So df dy, dy dx, and then from f to z to x, df dz, dz dx. Okay, ultimately, this is the thing we want. And in order to get by itself, we're using the fact that we know f of x, y, z is equal to 0, right? In order to define z implicitly as a function of x and y, we have to have an equation, right? So we put everything on one side, on the other side we get 0. So really df dx is going to be 0 because it's always equal to 0. Also, we said the partial of the function x with respect to x is just 1. And the partial of the function y with respect to x is 0. So because we had this initial, the way we're going to do implicit differentiation is anytime you have some equation which implicitly defines z as a function of x and y, it's some equation. So basically you put everything on one side and set it equal. So 0 is on the other side, right? So if you have stuff on both sides, just bring it all over to one side, and you have everything on the left-hand side is your big F, and then on the right-hand side you have 0. So big F is always equal to 0. So when you take the partial with respect to x, you're going to get 0. Does that make sense? Okay. So we want to get dz dx by itself. So we know, okay, so we have the partial of f with respect to x times 1, because we know dx dx is 1, plus 0, plus the partial of f with respect to z times dz dx is equal to 0. And so we just bring over, we get dz dx by itself. And when we do that, so we get negative df dx divided by df dz So in other words, negative partial of f with respect to x. Whoops, wow, that is illegible. Negative f sub x over f sub z is equal to the partial of z with respect to x. And then we can play the same game for the partial of z with respect to y. And we see when we do that, we get it's equal to negative partial of f with respect to y over partial of f with respect to z. So the way to remember this is, so dz dx, the partial of z with respect to x. So we have z on top, x on bottom. So the way we do that is you flip x and z. So you get everything on one side. You write f as a function of x, y, and z. You set it equal to 0. And you take the partial of that expression with respect to x and the partial with respect to z. So it's negative f sub x over f sub z. So for dz dx, we have z on top, x on bottom. So you negate it and you flip it. So negative f sub x over f sub z. Now you have x on top, z on bottom. And then same for dz dy. You flip the y and z, and then you negate negative f sub y over f sub z. And those are really, really quick to calculate. Much quicker than doing the usual method for implicit differentiation. So let's do an example. Let's use the example we just had. So x squared plus y squared minus 2z squared plus 12x minus 8z minus 4 equals 0. Let's calculate dz dy at 1, 1, 1. X is 1, y is 1, z is 1. Okay. So everything is conveniently already on one side. So this whole thing is going to be our f of x, y, z, our big F. And so we have our formula for the partial of z with respect to y. It's going to be flip y and z and negate. So we have negative f sub y over f sub z. And what is negative f sub y? It's going to be negative 2y. And then our f sub z is going to be negative. So x squared becomes 0, y squared becomes 0. Negative 2z squared becomes negative 4z. 12x becomes 0. Negative 8z becomes minus 8. And then negative 4 becomes 0. So then we plug in x equals 1, y equals 1. Let me write that down. We plug in x equals 1, y equals 1, and z equals 1. So then we get negative 2 over negative 4 minus 8, which is negative 12. So we get 1 over 6. And you know what? Let's do dz dx also at 1, 1, 1. So the partial of z with respect to x is flip x and z and negate negative f sub x over f sub z. So what is negative f sub x? Right, that's going to be negative 2x. So negative quantity 2x plus 12. So negative 2x minus 12. And then we already did f sub z. That's negative 4z minus 8. And then when we plug in x equals 1, y equals 1, z equals 1, so that's supposed to be an at, we get negative 14 over negative 12, which is 7 over 6. Okay, so implicit differentiation, really easy. Get everything on one side, set it equal to 0. Everything on the left-hand side is now your function of x, y, and z. So to take the partial of z with respect to x, you flip dz dx, flip x and z, and negate negative f sub x over f sub z. Same for partial with respect to y, flip, negate. Really easy, much quicker than doing it the long way, which we didn't even go over, but don't worry about it. Okay, any questions about anything today? It'll tell you. It'll always tell you which partial to take. Unless it's like a word problem. So I believe there's one problem in the homework where you'll have to write everything out. But in general, it's going to tell you the partial you need to take or the derivative, depending on whether it's a partial or not. But yeah. All right. All right. So have a great weekend, and I will see y'all next week. Later.
Thank you.
Thank you.
Professor, is this homework posted already, or is it going to be posted here shortly?
The chain rule one?
Yeah, just like what we just covered today.
Yeah, I'm going to assign it right now. So yeah, it'll be assigned in like 30 seconds. Yeah.
Hello, Professor Conrad. I have questions about the homework due tonight.
You have a question about the homework due tonight?
Yeah, so for the last two questions, for some reason, I think I have the correct answer.
Okay.
I typed the letter wrong. So